Alright, let's get started on this little video. You see a picture of my test setup, and I'm going to describe it as such. Over here, of course, is a Raspberry Pi 2 or a 3. In this case, I use my Raspberry Pi 2. This is a GPIO breakout board. This is a DS1307 clock, which is not the subject of this video. Two other videos will cover the I2C LCD display down here. The other video will cover this. This is an MCP4725. That's a 12-bit DAC that will be interfaced to the Raspberry Pi. The main subject we're going to be looking at is right here with the little purple board. It's an ADS1115. It's a programmable 4-channel analog to digital converter that's used under the I2C protocol. This little device, this little transistor looking thing, if you see it here, is the TMP37 centigrade temperature sensor. The idea that this demo, I'm going to walk you through the software and how to program the ADS1115, is it's going to read a voltage level off of this, and it's going to print out the temperature in Fahrenheit and centigrade on a terminal, along with other types of data. Couple of other things to note first. All three of these devices are connected to the I2C. An immediate issue that came up is I'm operating both of these devices, the DAC and the ADC. I'm operating both at 5 volts, and they have built-in pull-up resistors. This creates a bit of a problem with the Raspberry Pi, whose I2C lines are running at 3.3 volts. Now, one can go into the boards and remove the pull-up resistors. In my case, this little board right here is a level converter. It solves the problem. It isolates the pull-up resistor problem, and it also translates the voltage and works just fine. Like I said, all three of these devices, actually 4 of them, the clock, the ADC, the DAC, and the LCD display are all I2C devices. They're on the same bus. All right, let's move on. Here is the output on the terminal of the Raspberry Pi, where I took 5 temperature readings, and it put out the hexadecimal, decimal values, and the voltage actually coming off the TMP37 temperatures, centigrade temperature sensor. And of course, it calculated for me the temperature in centigrade and Fahrenheit. Like I said, this is done 5 times. The ASD1115 analog to digital converter channels, and there are 4 of them. In this case, I just use one, has a resolution of 15 bits. Or about, I think, around 120 microvolts per step. This is something like 40 times the resolution that you would get out of an Arduino. Very, very accurate according to my measurements. Here's a closer look at the ADS1115. It's the little circuit board that was, in the big drawing, it was just a purple spot, but it comes as a little circuit board. Here's the actual chip. This is the size they make it. They don't make it in a a larger size, so you're going to need some kind of breakout board. The entire breakout board assembly here I got for about $2 off of eBay. These are available from people at a higher price from Adafruit or SparkFun. In this case, I had to cut. They produced but largely libraries that you had to use with Arduino or whatever that didn't tell you anything about how to actually program it. I went into the spec sheet, and I will show you how to actually program the chip without libraries. or other people's code so you can understand how to do your own coding. Here are your electrical connections for the ADS1115. This came directly out of the spec sheet. Of course, you have your I2C with its serial clock and serial data. The board that I'd shown earlier has its own internal, already in it, pull-up resistors, which is 1K to 10K. The pins that you have an alert ready pin that you can run back to a GPIO. I don't use them in this demo because there are some sophisticated comparator functions that this will also do in addition to analog to digital conversion. It has some really neat comparator functions, and that's what the alert ready pin is about. It has an open drain output, I believe, and when the functions on a comparator, you can use it as a fancy comparator essentially. But what you have is 4 input channels, AN0 through AN3. Of course, you have 5 volts. You need a bypass capacitor. And these will operate from, I think, 3 volts to 5.5 volts. I use 5 volts on all of my stuff. And like I mentioned before, I had to use a level translator in order to isolate these pull-up resistors. I could have gone onto the little board and cut the resistors out. I didn't want to damage my board. So let's move on. One final thing to note is this address pin, pin 1. While in this case it's got it grounded, you can actually connect this particular pin, that is pin 1 itself. It can go to SCL, SDA, or VDD, and it gives you 4 addresses based on where this address pin is connected, and we'll take a close look at that now. All right, pictured here are the electrical connections. There's our address pin. In this case, it goes to ground, so its I2C address is 0x48. But if I took that same address pin and connected it to VDD, or 5 volts, my address would be 0x49. If I connected that same pin to SDA, my address is 0x4A. And if I connected address to SCL, or serial clock, my address would be 0x4B. In this case, I use 0x48. The ADS1115 has actually 5 registers, of which we're only concerned with 3. Before you can read a conversion or set up the configuration, you have to call the pointer register. Bit 0 and bit 1 select what you're going to be writing to or reading from, with 0 being the conversion register and 1 being the configuration register. Both are 16-bit registers. The other 2 registers that we're not going to cover here are upper and lower limit registers, which I left at default values. Let's take a look at what we got here. First, if at 0 we have the conversion register, this is a 16-bit register. It is read only. When you're doing single-ended analog to digital conversions, which I'm doing here, the resolution is actually 15 bits, not 16 bits. D15 serves as a sign bit when you're in the differential mode. Remember, this thing has some quite sophisticated comparator functions, so we're not interested in bit 15 as a single-ended entity. The config register sets up which channel we're going to be reading. It's going to set up bus speed and several other things. So let's look here real close. On your config register, bit 15, this is operational status bit. This is used when you're in the one-shot mode. The one-shot mode is you write to the configuration register, you wait for this bit here to either clear or set, then you read the conversion register for whatever the value is read. After that, what the single shot does, the device when you first power it up defaults to low power. It's essentially turned off. When you write to the config register, the device turns on, does a conversion, turns itself back off. If you don't use that mode, and that mode, by the way, is controlled by bit 8 over here. The next 3 bits here, mux 2 through 0, sets up your input. Here's what your input looks like. Here's your 4 inputs, and depending on which code you use, you're going to trip these internal CMOS switches. Okay, let's go back here. What have we got next? PGA 2 through PGA 0. That's programmable gain on your amplifier, which I'll show you what that is momentarily. Bits 7 through 5 control the bus speed for I2C, and 4 through 0, for example, they control your various sophisticated comparator functions. Here is your internal block diagram. Here is our mux switching. This is our programmable gain amplifier. We have the 16-bit ADC, voltage reference oscillator, and your interface circuit for the address, and I2C clock and data. Okay, let's have a closer discussion of bits 11 through 9. That's your programmable gain amplifier. This is only partial what's in the spec sheet. Note that you could have readings all the way up to 6.14 volts. Why they did that beats me, because you cannot operate this thing above 5.5 or you will blow the circuit. So you're never going to exceed 5.5 volts. I ran mine at 5 volts, so the one I have to use is the 4.096 volt setting. If you are operating yours at 3.3 volts, you're going to have to use the 2.048 volt setting, and here's the 3-bit code for the corresponding voltage measurements. All right, let's look a little bit closer what these numbers are going to tell us. In my case, running at 5 volts, I'm going to operate at 4.096 volts. Because I'm using a 15-bit resolution, that's 2 to the 15th power, is 32,768. So I have 4.096 volts divided by 32,768. This gives me 125 microvolts per step. Let's compare this to Arduino with a 10-bit resolution. 5 divided by 1023 is 4.887 millivolts per step. In other words, I have a resolution with the ADS1115 almost 40 times better than the Arduino, and it seems to be pretty accurate from my measurements with a digital voltmeter. Let's talk a little bit more about mode select. As mentioned earlier, it was bit D8. A 0 in D8 is continuous conversion. That is, once I write it and it runs, I can read it over and over and over. Just do reads continually, and it will update itself continually. If it's a 1, it's going to be the power down single shot mode, which means I have to, every time before I can do a reading, I have to do a write to the config register to wake it up, to get it to do a conversion, and check that bit at D15 to make sure the conversion has finished. Finally, let's just do a quick review of the program itself. Here's the libraries that I had to use. I had to declare the following integers. For instance, I set the address to 0x48. There's a file descriptor. And these particular int16 underscore t and so forth, all of these are special type integers that are used across various C platforms. I also had to declare a float variable. Then I set up my volts per step VPS, which we discussed before, 4.096 volts divided by 32,768. This was a constant float variable. Okay, this is what you normally do under C to open a device. It checks that it opened up properly. If not, it'll exit with 1, and that's the end of the entire program. Nothing else will work at that point. Here is where we link the I2C Slave Channel to the ASD address. You can read this in the program, which is available on the website. This goes through bit by bit by bit what I did with the bits in the config register. This is the 8 most significant bits. I had to set the write buffer to 1 to aim it at the config register. This is the 8 most significant bits. Write buffer 2 is the 8 least significant bits, and you can read what the different bits are used for. We're going to write these 3 bytes to the device, and now we're ready to go. In this particular case, making sure, you'll see this as you saw earlier on the output, the ADS1115 Demo will take 5 readings. That's what you saw earlier, way back up here. That's the message you saw there. Once again, I will write a 0 to it to make sure that my readings are aimed at the conversion buffer, the conversion section, and not the config. This is a while loop. Here I'm going to read 2 bytes from the conversion register. And what do I have to do? I'm going to have to change these a bit. When I read 1, I'm going to have to combine these into a 16-bit integer value. So read buffer 0, which has the 8 most significant bits, are shifted left 8 places and stored in val, and then I OR the 8 least significant bits. What this little thing does here, if a bit, it's plus or minus a bit. It's not, if it's minus a bit, it'll show up as a small value negative number. This eliminates that problem. Now, my float, I'm going to multiply val. That's what I got up here with these 2 bytes. And I'm going to multiply it by my VPS constant, voltage per step. The rest of this down here simply displays what you saw in the earlier terminal output. Here, I'm going to divide my float by 0.02. That's going to give me the degrees in Celsius. And then I'm going to take that over and use times 9/5 plus 32 to convert it to Fahrenheit. And it will output a number, as you saw earlier, something like this. It'll tell you the number of the reading, you're going to get the hex value, whatever it is. That's the hex 0x present 02x. That's this. It's going to give you the decimal, and then it's going to read you the voltage, whatever it happens to be. Then it's going to do the conversions, and there you are. It's going to sleep 5 seconds or delay 5 seconds before it does the next reading. When count reaches 6, we will break. Finally, at the bottom of the program, I'm going to change it back over to the power down mode. Here I'm writing these two codes here to your config register, and it will it will put it to sleep, saving the power. Then I'm going to close the entire I2C and return 0 and exit from the program. And that's it. So I hope this was useful and fun. Study the code and the web page very closely. This is a very sophisticated device. I also have links to the PDF manufacturer's file so you can read the spec sheets. Visit my website at www.bristolwatch.com. Have a great day.